cinema soundtracks have a particular thing about them. You mix them once, and then you play them everywhere. You mix it in one or more dubbing theaters that are set up and calibrated to the current standards, and you play them in a variety of exhibition theaters, all kinds of shapes and sizes, each having a different sound system, and all supposed to be calibrated to these very same standards. So theoretically, the soundtrack should sound consistent in all of these different venues. But quite often, it doesn't. Making a movie soundtrack consistent in multiple venues is a big challenge. Cinema sound is consistent between mixing stages, between the mixing stage and the exhibition theater, and even between exhibition theaters. And I'm sure if you've gone out to the movies and seen the same movie in various places, you know what I mean. Here's a diagram that gives you a little overview of what goes on in the theater. Everything on the left is the stuff that goes up in the projection booth, and we're not really concerned with in this particular presentation, which in the vernacular is called the A chain. The B chain is all the sound system out in the theater, the amplifiers, the speakers, the screen, the cinema acoustics, everything to do with what goes on out here in the cinema room. And we're going to go through a little bit about what each of these components are and kind of how they fit into the overall picture so that we can sort of get a better understanding of what the standards are trying to do and how people are trying to go about calibrating for consistency in these venues. First, we'll talk about the screen speakers. The screen speakers are behind the screen, so you don't see them when you come into the theater. These speakers are actually responsible for producing most of the sound that you hear. They have to be capable of delivering high volume levels across the entire audio spectrum with full fidelity, which is a very big challenge. They have to be capable of covering the entire auditorium. And in order to do both of those things, they're often set up in multiple boxes. They're in some cone speakers and some horn speakers. Newer designs might even be line arrays, such as what you might see at a concert. Here's some examples of some cinema sound speakers through the years for screen speakers. You can see they vary quite a bit, but basically they're large. They've got, you know, big horn on them, and they're trying their best to push a lot of sound out through a screen to the audience and cover very well. Screen speakers are not just stacked up on a couple of boxes behind the screen. Generally, they're put in what they call a baffle wall. So you actually, behind that movie screen, is generally a wall, and the speakers are mounted in that wall, and that gives the speakers a little bit more stoutness and stops all the reflections from happening behind them and allows them to project better straight out to the audience. The surround speakers, which are the ones that you see up on the walls of the theater, are generally used for ambience and the pan sound effects, you know, the car buys, the planes flying over, things like that. In general, these require less power and frequency range than the screen speakers, although in modern soundtracks it's beginning to challenge it because people are putting more discrete stuff in the surrounds now. They're generally much smaller than the screen speakers and are usually a single, two, or three-way speaker cabinet. And multiple surround speakers are used to get coverage. So if you look, you can see there's a number of speakers on the walls, not just one speaker, but it's several in every theater. And that's designed to kind of give you a surround effect and sort of cover the theater rather than be a point source. Here's an example of a few surround speakers. You can see they're of different designs. The one in the middle is a fairly modern design, which is designed to put out quite a bit more power, and we'll see why in a little bit in this presentation. The subwoofer speakers are generally used for the low frequency effects. Sometimes they put music in there and an occasional vocal effect or something with your, and these must deliver very high volumes in a narrow range of frequencies. Generally they have multiple subwoofer cabinets. These are generally kind of along the bottom of the screen. You usually don't see them in the theater. They're kind of tucked under the screen in a lot of theaters. You use a number of them to get the level that's necessary and to cover the entire theater. In general, the sound should be able to cross over from the low end from the screen speakers and down into the subwoofers with a similar perceived character, although we generally find that may not be the case. Here's some examples of subwoofer speakers that you might find in theaters today. Here's another example where it shows two 18-inch speakers per cabinet that are actually towed in toward each other, which actually has some efficiency. This has become a fairly common design. The amplifiers themselves should amplify and not color the sound. They are tasked with having excellent frequency and transient response. They have to handle sustained level, large peaks without clipping. And you need to match them with the speakers. So it's not just like you put in a kilowatt amplifier and just throw a bunch of level at the speaker. That's not necessarily the best way to get SPL out into the theater. You want to try to match what that amplifier does with what the efficiency of the speaker is. So this is in the realm of the system designer to do. The equalizers, every theater's got equalizers someplace. Quite often they're inside the cinema processor, but they can be a separate unit. It's very common to have 1/3 octave band equalizers, although parametric EQs are also possible and are becoming more popular. Modern equalizers can be controlled from a network computer, so you can just put your laptop up, plug into a network, and you can right there sit there and control all the equalization in the room, including the overall EQ and if there's EQ associated with the speaker crossovers. So it's gotten very cool. The screen itself is never friendly to sound. It has transmission issues. You can imagine trying to get sound through it, but it also reflects sound back at the speakers and into that wall we talked about, which creates all kinds of problems. One of them is a smearing type of an effect. So traditional perforated screens, which you see in most of the theaters today, have little perfs all through them to allow the sound to come through. Generally, you have to have some high frequency compensation to get any treble frequencies through there. The silver screens that are used for 3D are even more challenging because they're really thick and they're not friendly to sound at all. There's a new design screen called a woven screen, which is actually fairly promising for sound. The cinema room acoustics are a big part of what happens because you're putting all this sound out into the room, but what the room does with it is extremely important. It's very important to design the acoustics in the room from the very beginning for cinema and to make it work right. The room reverberation should be short. You generally have to damp the walls and floor and do some treatment to the room. You have to be very careful about the close reflections and the slap sound that can happen in rooms. These interfere with the perceived imaging of what's coming at you and also the intelligibility of what's coming at you. Here's a little diagram that I got from the Leonard Audio website, which I think is cool. It shows kind of your basic theater setup with the 3 speakers in the front, a subwoofer. You can see the surrounds on the wall, and you can see what's trying to happen. These 3 speakers in the front are trying to make a coverage pattern, and there's all kinds of slap echoes and things going on around the auditorium. So by the time you get into the audience, if you're not careful, it can just be kind of a chaotic situation. So it's very important to treat the cinema room acoustics seriously. And the big mantra is set the system up from the beginning, let an expert do it right, and from then on you're going to have a lot less trouble. You have issues with, somebody's got to figure out the cinema system, design the acoustics, install it, figure out the coverage angles, calibrate the crossovers, put the surround delay, the subwoofer and screen alignment, the electroacoustic calibration, and SPL calibration. Definitely leave it to an expert. So let's take a minute here, and I'm going to give you an overview of the current standards that exist in the area of cinema sound. These standards actually kind of began in the 70s and have had some updates along the way. The current reigning standard for electroacoustic response is called the SMPTE ST202. The SMPTE recommended practice is to deal with the sound pressure level, which is the amount of sound that's coming at you, calibrating that accurately, is SMPTE RP200. And the current recommended practice for audio reference levels is SMPTE RP155. And we're going to touch on each of those here as we go along. These standards that are around today are built around measurements using wideband pink noise as a test signal, 1 or more calibrated microphones, a 3rd octave real-time analyzer, and a sound pressure level meter set to C weighting and slow response. And we'll go through this in just a second. Pink noise is kind of differentiated from white noise because pink noise has equal energy in every octave of the audio band, whereas white noise has equal energy in every, completely across the whole spectrum. so that line would be flat with white noise. In SMPTE 202, they describe a method for how to go about miking up the room and calibrating it. So with the screen on the left side, you go 2/3 of the way back into the position that they call S. That's 2/3 the length of the auditorium, and you put the microphones within this area in here. The microphones themselves, there's some preferred characteristics for those. What you want to use is calibrated pressure-sensitive omnidirectional mics with a 1/2-inch capsule or smaller. 1/4 inch is actually typical. In a mixing stage where the mixers are, you place the microphones behind the console at the positions where the mixers and producers would be, because you want to optimize for that position. And in exhibition theater, you put it at that S position that I just showed you, and you put like 4 other microphones around the room to try to capture an average. And the specs in 202 indicate that these microphones should be 3 to 4 feet high, greater than 6 inches above any seat, 3 feet apart, 16 feet from the screen, 5 feet from the walls, actually greater than 16 from the screen, greater than 5 feet from the walls, and 90-degree angle, which is straight up. Here's another little picture that shows you a group of 5 microphones out here. Here's the microphone in the S position that we just talked about, and screen's over here. This kind of shows you maybe like seats going up here and microphones are pointing, so it's just gives you another little look at the situation. When you panel these microphones out there, you do a process called spatial averaging in order to try to average out any errors that you have and figure out how the sound is covering the room in an average fashion. So there's a couple ways you can do this. You can measure multiple mics one at a time, which is called multiplexing, store those and then average them. Or you can measure one mic and just move it around to a bunch of positions and temporarily average those. All of this information is fed into the real-time analyzer, as I mentioned, and this is generally done in 1/3 octave bands, and the result that you get from this is called the electroacoustic response. By employing slow averaging, so because you can imagine pink noise, everything's kind of bopping around on the screen, so you kind of slow down the display, and you can kind of what they call smooth it, which will show a curve. Here's kind of an example of what this might look like on a screen. Each of these little bars is at 1/3 of an octave if you look across the bottom here. And these are some figures that are just drawn from those. Each of the values on the top are represented digitally there. And you can kind of see that if you were just to take a curve and just draw a line along here, you'd end up with something that looked kind of smooth. So the SMPTE standard 202 shows you what that's supposed to look like using this graph here, which has been dubbed the X curve. This one here is shown for a medium theater from like 200 to 500 seats. And it shows what the response is supposed to look like. And again, of course, this line is a kind of a, it never looks like that on a graph, let's put it that way. It's like that kind of smoothed average I just talked about. And you have a range of plus and minus 3 dB that this can fall in. So it's not necessarily that you're trying to nail it straight to this line. You're trying to get it in the zone between these two dashed lines. There is room size corrections. Smaller rooms show a little bit more high-end response. Bigger rooms show a little bit less response. And this graph down here kind of shows you how that goes by number of seats. So what are the response characteristics of electroacoustic response? You have to understand that it's a steady state response. It doesn't tell you anything about how transients are going to go, how quick sounds are going to respond. You put the pink noise out to the room, you kind of wait for everything to get steady, and then you make a measurement. It's also very important to realize that what you're looking at is the response in the room. You're not looking at the response of the speakers. The speakers themselves, if you were to measure those, look very, very flat. But once you get it out into the room, and you have kind of a combination of direct sound and reverberant sound, that's the kind of shape that you end up getting. There's a few things that affect that. There's high frequency attenuation. Just as sound goes through the air, it attenuates. The screen itself, of course, attenuates high frequencies. And temperature and humidity can affect the way that these things read. The characteristics of the X curve itself is flat from 50 to 2K in medium room. rolls off at 3 dB per octave from 2 to 10, 6 dB per octave roll off above 10K. At the low end, it rolls off at 3 dB per octave below 50. And like I said, the overall tolerance range is plus and minus 3 dB, a little bit more at the low frequencies. Taking it speaker by speaker, the screen speakers are supposed to match the X curve within 3 dB. The surround speakers generally extend the flat response to 4K or a little bit higher because they're actually closer to you and don't have to go through so much space, so it actually flattens out a little bit. The subwoofer has a narrow passband, and they spec it from 25 hertz to 120 hertz within 3 dB. And the expected screen and surround speaker electroacoustic response is subject to the room size corrections, as I mentioned. So once you have all these microphones up there and you're taking these measurements, this is just a quick overview of what you would do. You take a look at the system integrity, make sure no speakers are blown, nothing's distorting, everything's basically in shape, polarity's right. You take the wideband pink noise that we just talked about, put it into the system at the reference level, which I'll talk about in a second, one speaker at a time. Check your crossovers, adjust those first, and then you apply system equalization as necessary in third octave bands to bring the electroacoustic response within the spec tolerances that we just mentioned. Parametric EQ can also be used. After you've got this electroacoustic response figured out, now we try to go in and figure out the actual sound pressure level that we're going to get in the theater, and we calibrate that. Sound pressure level is an average taken across the measured bandwidth. So if you look at the bandwidth of the audio spectrum, they divide up all those little bars that you saw, they measure the energy in every one of those, and then they average it across the whole thing. And this gives you sort of an overall picture of what the SPL is as your ear might hear it. The expression of SPL is the number of decibels above the threshold of hearing. This average is weighted to account for how we hear. So A weighting mimics how we hear kind of medium level sounds. Our ears are much more sensitive in the upper mid-range, not so sensitive in the low end, not so sensitive in the high end. C weighting mimics how we hear sounds when they get very loud, which is much flatter and just rolls off at the low and high frequencies. And C weighting is what we're using in the current standards. So the audio reference level for doing all of this work is minus 20 decibels on full scale on a digital ppm meter. That means that digital, as you may know, has an absolute maximum that it can't go over. So when you fill all of the bits in a digital word, it gets to what they call zero or full scale. What we do is we set the reference level 20 dB below that. So that gives you 20 dB of headroom. On a cinema processor, this looks usually set it to a value of 7, or some cinema processors actually have 0. This indicates unity gain. And here's a happy cinema processor that's showing you it's at 7. So continuing on with the highlights, how do we go about doing this SPL measurement and adjusting it? Well, like I said, after you've done the electroacoustic calibration, you start up with this, use the same microphone setup, inject the wideband pink noise again, you do it one speaker at a time, and then the gain of each speaker is adjusted like this. Each screen speaker gets 85 dB C weighting. Each surround array, which is all of the surround speakers, not the individual ones. So there's one array on the left and array on the right. Those are set to 82, and then the subwoofer is set to approximately 91. Here's some handheld meters that are often used to do this SPL rather than going out and having to set up that whole microphone setup. The one on the right is the ubiquitous Radio Shack meter, which has been in use for many years in dub stages. The subwoofer has a particular thing. The reason I had a star next to it, you don't just set it for 91. What you're really doing is setting it for 10 dB higher in its passband than the value of the screen speakers. So now we come to the challenge. How do you achieve consistent results with these standards? Standards by nature look great on paper, but applying standards in the real world can be really challenging. There's many factors that can cause inconsistent results. Technicians have different equipment, they have different approaches to it, the pink noise signal itself varies, microphone responses vary even though they're calibrated, cinema sound systems totally vary from place to place, and every theater space has its own character. No two rooms are exactly alike. So in general, achieving sound consistency through replicating measurements has issues. Our ears don't hear like the measurement data. Measurements will look different depending on where you put the mics in the room and the characteristics of the room. But our ears and brain compensate for that sort of stuff, and measurements don't compensate for it. A flat speaker system, when measured in a cinema reverberant space using the methodology in 202, should measure similar to the X-curve. We already talked about that. The reverse is not necessarily true. Equalizing the system to strictly match that X-curve target on an analyzer does not automatically result in a flat system response for all the reasons that we just mentioned, and certainly doesn't necessarily guarantee a good sounding system. So there are some performance challenges in addition. I talked about that 20 dB worth of headroom. So we've got 20 dB of level above the reference. So that means that if you get up close to that 0 dB level, the screen speaker has to deliver 105 dBc cleanly to the audience, as measured 2/3 back in the auditorium. Much smaller surround speakers have to deliver 102, and the subwoofers have to deliver over 110. These numbers are at the extreme edge of what many sound systems can do, and many of them can't do it. So having looked at the general situation with sound systems and kind of what we're up against, I'm now going to go in and talk about some of the new systems that have hit the market, which have gotten the coin of immersive sound systems. Some people call them 3D. Several of these have hit the market recently. Some of the characteristics are that they make the entire auditorium part of the sound field. Most add the additional dimension of height in some way. All of them have additional surround speakers. Some have additional screen speakers, and some have additional subwoofer speakers. So I'm going to go through some that are on the market today in alphabetical order and just kind of describe some of the basic characteristics of these. If you want to know more about the specifics of these systems, I suggest going to the websites for these manufacturers. They've all got white papers that'll give you real nitty-gritty, but I'm going to give you a little overview here. The RL3D system is a layered approach to doing immersive sound. They take the regular system that we've already got, which is the 3 in the screen and these here, so they call this the lower layer. They add a layer right above it that's pretty much just like it. That's called the height layer. And then they also put speakers on the ceiling, which they call the top layer. And then through this is the way that they attain their sound. Most of the releases in RL3D are 11.1, but you can also do 13.1 and 15.1. The Dolby Atmos system takes a different approach. It has 5 speakers behind the screen, which you can't see. It adds some surrounds toward the front. These 2 here and these 2 here are added compared to the regular 5.1, which probably wouldn't start till here. And then the main characteristic is it's got these speakers on the ceiling, 1 row here and 1 row here, which are called the top surrounds. And so in Dolby, you set up a bed across all the regular speakers on this level and here, and then you have particular objects, which is just any sound that you want to assign to it, that you can put any place within the room, and this is how this system achieves its immersive sound. The ISONO system, which has actually been around for a while, takes a very different approach. It rings the entire theater with speakers all the way around and uses a method called wave field synthesis to kind of holographically place an image anywhere within the room inside of this ring of speakers. And the newer designs of ISONO also add ceiling speakers, but they're not pictured in this diagram. The NHK 22.2 system has been around quite a while. You haven't seen it too much over here in theaters. There are some theaters in Asia that have it. And this is actually being kind of moved toward the UHD TV area, but I wanted to show it to you anyway. It also takes a layered approach. There's the middle layer of speakers, which are kind of similar to what we have. There's 5 across the front and surrounds and back. And then it adds an additional layer on the top, and 2 subwoofers on the bottom, and there's no height speakers, no top speakers in this system. And lastly, the sonic tier system has kind of an approach in between all of these. They have actually 3 layers of speakers behind the screen, as you can see. Then they have a regular number of surround speakers, although they do add the front two, as Dolby does. And you see the same kind of idea with speakers across the ceiling in 2 rows. And this system is popular right now in Korea. There's a lot of movies have been released in this format in Korea. So with these systems comes new performance challenges. The desire to make all of the cinema room part of the sound field puts a higher demand on the surround speakers than in traditional systems. In order to more closely match the frequency response of the screen, they base manage the surrounds, which means that you put subwoofers up in an attempt to extend the frequency response that the surrounds can't do into the subwoofers. These particular subwoofers will likely require different characteristics than the one up in front of the theaters. There's installation challenges with these systems. Each system has its own concept of how to attain immersive sound. There's challenges when installing into any given space to obtain the desired effect. Aiming of all of these speakers is critical and is very dependent on the room. Dubbing stages, again, will optimize for the mixer position. Exhibition theaters will try to cover the whole theater and give everybody an immersive sound. So we have more speakers, more detail to consider. Immersive sound systems also present new challenges in the standards process. Right now, no B-chain standards exist. Height is an uncharted standards territory. We've never dealt with it before. Human beings don't hear height nearly as well as we hear the front and the sides. Standards for the base management of the surrounds I just mentioned we don't have. And we need some overall performance parameters so that installers and manufacturers have some guidelines. On the side of actually delivering the audio, we don't have any standards for soundtrack mastering. There's not a common file format that everybody's mastering to. We don't have a standard for delivering immersive audio to the theater. In some cases, special DCPs have to be created. And we need some standardized file formats if we're ever going to archive this and pull it out later and play it. So what are you going to do about it? That's what I'd like to know. SMPTE is on the case. The Theater B-Chain Study Group was formed in March 2010 to study the situation. This group produced a set of recommendations for new standards that was submitted to the SMPTE Standards Committee. And based on that, the SMPTE Standards Committee formed a new technology committee, 25CSS, in October of last year. This is the very first SMPTE Standards Committee dedicated solely to cinema sound. It doesn't mean it's the first audio committee or the first committee that's ever dealt with cinema sound. It just means it's the first committee that was absolutely dedicated to making standards for cinema sound. And I think this is great because it indicates a strong commitment to cinema sound as being 50% of the music experience, which I say is about time. So our project goals, we think that the sound standards of the future must be built on concepts that more closely model how people hear. New measurement and calibration techniques must be developed that are tailored to human perception. These must be able to be performed in a straightforward way to achieve consistent audible results. And we also need to develop cinema sound system performance parameters which we do not have now. Okay, so plan of attack. Our first wave is going to be to optimize current methods of doing things. The second wave is going to be moving forward from there. Third wave will push the envelope, and then we'll set the stage for the future. In our first wave, to optimize the current methods, we've put 4 subgroups together already. We have an ad hoc group to deal with modern measurement and calibration. Their output's going to be a recommended practice that has a step-by-step procedure for cinema sound system calibration, which will essentially be a best practice using current standards and modern measurement technology. As you can imagine, the standards that are in place were written quite a while ago. Technology's come a long way. We've got new machines, new analyzers, better mics. We have all kinds of things. So we want to kind of document that and what the best practices are today. We want to deal with actually creating a standard pink noise signal, because as simple as it sounds, we don't really have one. It used to be that we had test films that SMPTE would sell, and they would have pink noise on them, and we used those to set up our sound systems. But since the move to digital, we haven't really had that. So this committee is going to come up with a standard pink noise algorithm, and in the process, they're going to create an audio file and a DCP and a reference implementation. So we'll actually have these things to use. A third ad hoc group is going to go back into that data that the B-Chain study group collected, which is pretty massive, and do a very detailed report and compare what we got from the data, make some analysis and conclusions. This will be a good seed report for future work. and a study group on the immersive sound systems, which we just went through. We need to look at both aspects, the B chain and the distribution, as I mentioned. They're going to make a report to recommend standards, and they'll also create some work statements for a group to do this common audio delivery format and B chain parameters and calibration standards. Our second wave will be moving forward. Now that we've got these 4 groups and their output, we're ready to start the next phase. The first thing we're going to do is collect all the information from the first 3 groups and do a little study about how we can approach new electroacoustic standards and calibration methods. So that group will make a project plan. We'll make a group to deal with this common delivery format for immersive audio, and we'll do another group to deal with the B-chain sound system measurement and calibration for immersive. And then the third wave will actually take all of the stuff from that study group and the 3 groups before and start to go and make new electroacoustic standards and calibration methodology to replace the current ones. And we will also, in parallel, start up a group that is actually going to take a look at what the performance parameters need to be for cinema sound systems, because at this point, as I mentioned, we have no standards for those. In the future, we'll do some work on cinema acoustics and come up with some standards and recommended practices for that. There's also a group of people that are interested in figuring out a way to calibrate how loud soundtracks are, so that'll be something we'll probably look at in the future. And the crystal ball, well, I'm not sure, but there's plenty to do in the world of sound. And our ultimate goal, to make impressive and consistent cinema sound. It's going to take a village to do this. The standards are very entrenched. We've been doing things the same way now for 30 years. So in order to make any kind of change at all, we're going to have to get the mixers, sound designers, engineers, studios, manufacturers, exhibitors, everybody together to participate in these standards in order for them to be relevant and for anybody to adopt them. The proponents have to demonstrate the benefits of doing this to the key industry players, and then we have to develop a transition plan and a timeline that works for everybody, which cannot interrupt any movie production and distribution. So that'll be an interesting implementation that we'll need to come up with. So in summary, sound reproduction can vary by venue. Cinema sound systems have innate requirements and challenges. Calibration using current standards and practices does not always produce consistent results. The immersive sound systems produce additional challenges. SMPTE is working to create new standards, and the industry is going to have to unite in the creation and adoption of these new standards in order for them to make any difference. It's our village. If you want it to work, join us. Here's 3 ways. Here's how you do it. You can join SMPTE, join the standards community, join our group. If you feel you have something to contribute, please join. And I'd like to thank you on behalf of SMPTE.